Hi everyone, this is Dr. Pavel Ramirez Lopez, commenting from Esberga Mefos in the north of Sweden. Mefos is a metallurgical research institute founded in 1963. So as you can see, we are celebrating 50 years of research for the Scandinavian and world's iron and steel industry. My work here as senior researcher is primarily related to continuous casting of steel, flow simulations and other metallurgical processes by combining numerical modeling to plan trials and physical experiments that improve the productivity of these processes and the quality of steel products. In total, I have worked in this field for around 12 years, and although I am originally from Mexico, I have been working mainly in Europe, in England first, and now in Sweden, where Mefos is based. Today, I would like to comment in our recent publication on iron and steel making, which is entitled The Butterfly Effect in Continuous Casting. First of all, this came as an idea a few years ago by my former professor, Peter D. Lee, while he was still at Imperial College London, in England. He is now at Manchester University. The main idea was to draw some parallels between our research and modeling of the casting process and the chaos theories developed by Edward Norton Lawrence. So this was a good chance to revisit his theories and try to use them to explain some of our observations regarding the process. If you look at the title, it pays homage to the famous Lawrence question about complex meteorological systems. Does the flap of a butterfly's wing in Brazil set off a tornado in Texas? Which came to be known as the butterfly effect. This phrase denoted how difficult it is to predict the behavior of a complex system, such as the weather, where there are innumerable initial conditions, such as the flight of a butterfly, which we are not aware of, or are just too small to account accurately in our systems. Moreover, the number of factors or conditions involved in the system, also known as variables, is huge. And add that to the fact that some of the physical phenomena involved are very random themselves, such as turbulence, and you will end up with a chaotic system. This problem symbolized very well some of our observations during the industrial operations, where many of the steel makers see that apparently the same initial conditions in the plant can lead to two completely different results. So they often come to us and ask why two identical steel grades in the same machine, the same casting conditions, pretty much the same operation, will produce in one case a good product and in another case a catastrophic rupture of the strand known as breakout. To address this problem, we developed a numerical model, which we describe in the paper in Iron and Steel Making. This model provides values of heat flux, powder consumption, oscillation marks, and so on, which are in good agreement with those measured on the plant. One key factor is that our model tries to include the chaotic behavior of the metal flow, ergo turbulence, which is also one of the main sources of randomness in Lorentz weather systems. However, our model will not predict the exact time when the butterfly effect will result in the formation of a defect or a catastrophic breakout. What we learned was that the model can reveal the risk of such a defect occurring and help us to identify the most important factors causing it. A direct analogy between the butterfly effect in meteorological systems and continuous casting can then be made, including the unpredictability of the process and the chaotic behavior of many of the phenomena during the cast, such as turbulent flow, heat transfer, and irregular solidification. As Lawrence himself wrote, it seems appropriate to call a real physical system chaotic if a fairly realistic model, but one with the system's inherent randomness suppressed, still appears to behave randomly. Just as tornadoes can be hypothesized to arise from the flapping or not of the wings of a butterfly, defects on continuous casting may arise from a variety of sources, but can converge into catastrophic events, such as breakouts, when the particular frequencies combine. such is the case of turbulent fluctuations that combine with heat flux variability to produce deep oscillation marks and finally lead to cracks, hot tearing, or breakouts. A number of phenomena with a tendency to chaotic behavior, such as turbulence, are kept on the edge during industrial operations via sophisticated control systems. However, small deviations from the operational window, in this case from initial conditions, can unleash a chain of events whose singularities or particular defects are difficult to predict by numerical models. Nevertheless, numerical models can be a useful tool in understanding the possible causes of such behavior and provide a good benchmark to test solutions. As a matter of fact, we have to learn how to deal with chaos because it is an inherent player in many of our modern steelmaking processes, and I would say in many of our industrial processes. There is no better way to end this short comment on the paper than to quote Lawrence himself. Earlier investigators had occasionally encountered behavior of this sort, but usually under rather different circumstances. Often, they failed to recognize what they had seen, and simply became aware that something was blocking them from solving their equations or otherwise completing their studies. My situation was unique in that, as I eventually came to realize, my experiment was doomed to failure unless I could construct a system of equations whose solutions behaved chaotically. Chaos suddenly became something to be welcomed, at least under some condition. This is part of Lawrence's book, The Essence of Chaos.